In class, we talked about polymers. We introduced the concept of how we take these monomer units and we link them together to form a polymer. We're going to look at the different types of polymers in this discussion. We're going to be looking at the plastics that you would be familiar with in your everyday life. So let's begin by looking at the first one. Well, actually, let's begin by just talking about how we get those different polymers. Now, in class, we took a monomer unit and we linked it together to make the polymer, and we saw that as you changed what's linked up on here, those groups, you end up with a polymer with that group getting repeated over and over again. So it really depends on what we have placed here that will define the polymer. Now, before we broke and before we started doing the activity, we talked about if all of them were hydrogens, then you would have the monomers. It's called ethene, okay? And why would it be E-N-E? Well, it's because it has that double bond right there. So we're familiar with that language. This is its more common name, ethylene, okay? So this was an older fashioned name, ethylene, for it, where we learned to call it ethene. So if you start linking those together, one right after another, then the polymer gets named polyethylene. And we looked at polyethylene before we started our group activity last time. Now, if what we see right here is a Cl instead, a chlorine, okay? So that would give me a monomer, which is called chloroethene, which would be the name that we learned to name it. But its old-fashioned name is vinyl chloride, and very often the polymer's name comes off its more old-fashioned name. So this is polymer called polyvinyl chloride, but you would hear it called PVC. PVC pipe is a very common type of construction material for hot water pipes, cold water pipes in a home. So here's some information about PVC. So the polymer itself is going to have tens of thousands of these monomers linked together. So we have one monomer that looks like this, right? It's got 3 hydrogens and a chlorine, and then that gets linked to another one, so it's got 3 hydrogens and a chlorine. But this is going to go off in that length for many, many thousands hooked together. So like I said, this is in building materials. These are in piping that they used in water that's going to the source, going to your sink, or coming away. And it is going to have, okay, in that recycling triangle that we see, it's going to have the number 3 in it. So when you see that 3 on anything that you're dealing with, that is PVC. Now, PVC can't, you know, you got to have a source of recycling for that, but that's the PVC. Some other information about PVC is it is typically very, very, very rigid. But if you look at that water hose, which they're saying is made of PVC, it is not rigid. You can see, of course, it's looped around on the rack there, and it would be very helpful if it was a nice rigid pipe for a water hose. So the way they take PVC that is very, very rigid and very, very strong is they add what's called a plasticizer. Now, plasticizers are stuff that would be mixed into the process of PVC as it's being constructed, so it is embedded within the molecules. It's mixed in there. And that mixture and those plasticizers give it the flexibility that you need it to have for something like a water hose. Okay? So what this will do is it will allow those long chains to kind of slide past each other a little bit and not be connected in such a way that they cannot slide past each other. And that motion, so these are just representing the long chains of the polymers. So I've got several long chain polymers. With the plasticizers between those long chains, they can then slide past each other, and that gives it the little bit of flexibility that you would need in order to make a what we would call, quote unquote, a rubber hose. Okay, plasticizers are what give you that new car smell. When you get into a new car that has got vinyl seats, those and you're like, oh, I love that new car smell. Well, the new car smell is the plasticizers that are just slowly kind of leak out a little bit from the plastic, from the PVC that's in those plastic seats. and we use the word vinyl kind of loosely here. They might put plasticizers in all kinds of different rigid plastic materials to give it flexibility. So a dashboard that's made out of the material might eventually crack, or your seat might eventually crack because the plasticizers have slowly leaked out, and in the course of that happening, it gets more rigid, and then it's susceptible to cracking. All right, the next polymer is polypropylene. So we have to start with a propyl compound. And what does propyl mean? Well, propyl means 3 carbons, right? So let's get up here and look at 3 carbons. So we have 3 carbons, and because we have that ENE ending, we know we have a double bond between 2 of them there. Actually, they've got it drawn right here, but we wouldn't necessarily think about drawing it that way. So we would have drawn it like this. We only put 1 hydrogen on that, and we'd put 2 hydrogens on that. So that's kind of what we got used to doing. But isn't this down here the same thing? We've got 1, 2, 3 carbons. I have a double bond between 2 of them. Now down here we've shown it between the first 2. And what that means is this is one of the groups that's coming off of it. Instead of a hydrogen, like it would be for polyethylene, or a chlorine, which would be for polyvinyl chloride, now it's a methyl group. And that methyl group is going to be on every other carbon. So for some reason, this textbook image put that methyl group pointing down. But there's the 1, 2, 3 carbons, the 1, 2, 3 carbons of that monomer. Then you've got the 1, 2, 3 carbons of that monomer, and the 1, 2, 3 carbons of that monomer. So that is polypropylene, which is made up of propene, repeated over and over and over again. So some information about polypropylene. Polypropylene is going to be stronger than that high density polyethylene that we talked about before we started this lecture online. It has more rigidity to it and will hold up to pressure better. So it can withstand high temperatures. So you can put it into your dishwasher without distorting it. For the polyethylene, if you put it in the dishwasher, it's going to disfigure, and you can't put it in the dishwasher and have that high heat. But things that are made of polypropylene, you can place in the dishwasher. They can withstand those higher temperatures, and they're not going to distort on you. Another thing about polypropylene is you can pull it into fibers, and as you draw it into fibers, you're making threads out of it. And so these fibers could be used to make ropes. It could be used to make indoor carpet. AstroTurf would be made of polypropylene. The next polymer we want to look at here is polystyrene. Now you'd be familiar with polystyrene when you think about coolers, and then we've got a picture of a cooler right there. Okay, when you look at coolers, styrofoam cups, when we use the word styrofoam, this is polystyrene. That's its more chemical name for it. But there's other things that you see in the image there are made up of this polystyrene. So what is hanging off of that 2 carbon grouping with a double bond between them? Well, it is this group right here. Okay, that is a benzene ring, and a benzene ring that is attached to a carbon is called a phenyl group. All right, we don't really have to know that yet, but that right there gives us, if there was a double bond here instead and it's not the polymer anymore, okay, if we looked at that, that's the monomer unit of this thing. So we have this group off of one of the carbons. So the other 3 are the other 3 spots are hydrogens. So we take and we get rid of the double bond, and we convert it to a single bond there, and now we link them one right after another, and we have the styrofoam. Because of this large group, it's able to kind of fluff up and have a lot of air between the chains of these molecules. So here we see that it is described as transparent, hard, and brittle. And yet everything we're looking at here is not transparent, hard, and brittle. So how do they make it like that? We'll get to that in just a minute. We can use the word thermoplastic because it can be heated up and molded into various shapes. So it's being molded into a shape of a hat here just by warming it up and shaping it. But these guys are made of polystyrene, and we would see these as being fitting this description of being transparent, hard, and brittle. a case for a CD. Plastic forks, although there are white plastic forks out there, those clear plastic forks would probably be polystyrene. They would have the recycling symbol 6, okay, inside of its symbol there, if it is polystyrene or styrofoam. So you'll know you've got that. If you kind of examine different plastics, you're going to know what kind of plastic it is. So how do they make the foam? Well, what they do is they puff it up with air, so that as it is forming, they're also blowing air into it, and it's going to give it this fluffy texture. And it goes from being a clear, where you can see through it, to a white. Now both of those we call colorless. They have no color unless you put some color into them. But if it gets fluffed up like that with that air, then it's kind of a foam, and foams are colloids. So this is a kind of a solid colloid here. So that is how you make this styrofoam. Teflon and Gore-Tex are two names of the same polymer, okay? Teflon you've probably heard of. I'm not sure if you've heard of Gore-Tex, but both of those are the same compound. So let's look at the monomer that makes this compound up. All right, so the monomer would be where you've replaced all the hydrogens with a fluorine. So the monomer has a double bond, has a fluorine at each spot. Okay, so that would be the monomer. If you repeat it over and over and over again, you're going to get a long chain of this. Now, what is unique about this? Well, we just did the monomer, so we've already answered that question. This would be the other way of drawing that, of course, putting the fluorines right after the carbon instead of having them draped off like I've done in the picture above. This would be its chemical name because we use the word poly with it. It has 4 fluorines, so it's tetrafluoro. This is tetrafluoroethylene. That would be its old-fashioned name. Now, what would be the naming system that we use? We would call it, I don't think we'd have to have the numbers 1122 because there's no other choice. So we could just call it tetrafluoroethene. Okay, tetrafluoroethene. Don't need the 1, 1 and then the 2, 2 because if there's 4 fluorines, it's their only choice of where they can be located. So that would have been the system we learned, but this tetrafluoro, notice that ethylene ending, that is kind of the old-fashioned way. So PTFE would be its chemical name, polytetrafluoroethene. But we don't, in the world of chemicals, they don't call them that, okay? These are the terms for those substances instead. Now, what's unique about them is they're very stable against chemical attack. So you can coat things with this Teflon, and it will keep it from whatever's underneath that Teflon from getting attacked by chemicals. In the laboratory, in the chemistry laboratory, we have these little things called stirring bars, and they're magnets, and they're coated with Teflon, and you can stick them down in the bottom of a beaker. You can put a magnet underneath it that rotates around, and it'll cause the magnet inside to stir without you having to stir it. So it's a lazy way to stir. In that process, they have that coating of the Teflon because that stir bar is made out of iron, so it's magnetic, and that iron could easily be reacting with whatever was in that flask. So you don't want it to have that happen, so they coat it with Teflon. Where you would experience Teflon is there's a lot of cookware that is coated with Teflon. It gives it a very slick surface so things don't stick to it. In order to stick to it, there has to be some kind of chemical bonding that occurs, and this prevents that chemical bonding from occurring. It is also able to draw it into fibers. So you take that Teflon, and as it's warm, you can pull it and stretch it out into fibers, and it can be the threads of what we call Gore-Tex. Gore-Tex is a fabric that is a very breathable fabric. It lets in an air to come in and out of that fabric, but it will block the moisture from coming in. So if you perspire, that is able to actually it's got enough pores that we can have little bits evaporate out. But if you have big drops of water that are coming down from rain, like we see in the picture there, big drops of water, they would just sit on the surface and they would not penetrate through. So you can stay dry but still have a little bit of an opportunity for evaporation from your skin, okay? So It has to do with the size of the water. The evaporation of molecules inside of your skin are very small, and they can fit through the little pores and make their way out. But because a drop of water is very big and the water molecules attracted to each other, they're not going to seep back in through and make you wet. Okay, so that is Gore-Tex. Now, some properties about plastics in general. They have two different types of solid states depending upon temperature. And this is true for most typical plastics. There is at the higher temperatures, they're flexible and they're bendable. Below that temperature, they're rigid. Now, each plastic has a different place where that is, okay? Some plastics at room temperature are flexible, but if you put them into the freezer, they'd get too cold and they can become brittle, okay? So that would be a temperature where it's below room temperature, where it has that transition between the two. Some plastics at room temperature are very rigid and they don't bend, but you warm them up, let's say to 60 degrees, and they start getting some flexibility to it. So that temperature where it transitions between those two states is at a higher temperature for other plastics. As you add plasticizers to it, that changes where that temperature is going to be for that plastic. That temperature, so that's what I'm saying here. At high temperature, it's brittle. It's flexible, and we would call that more of a rubber state. Now, rubber is a actual name of a kind of polymer, a natural polymer, but that flexible state we call the rubber state, and the other state, when it's brittle, we call the glass state, and that's because it breaks. So the rubber state and the glass state, it is not a rubber, it is not it is not glass, but we use that term because it describes very well this idea of being brittle, shatter, versus being flexible like rubber is. We call this transition between the two the transition temperature, T sub G, okay? So when you're talking about a plastic and you use the phrase T sub G, you're talking about that temperature which it goes from being a plastic, brittle, glass state, but above that temperature it would be flexible like a rubber. So what's happening, okay? As the temperature rises, what we know about the molecule itself is we have two regions here, okay? We have regions that are very ordered. You see how they're kind of lined up? And you got regions of the plastic that are very disordered, okay? And that is if you've got something that it's not flexible. I mean, it is flexible and you can stretch it. So as the temperature rises, the distorted region starts to melt. And as that distorted region starts to melt, they're able to line up and get organized and then be able to stretch further. So that's what's giving flexibility. You warm them up, those disorganized regions can turn into a more organized state because of the motion of the molecules, and then it gives it that ability to stretch and be flexible. So as I stated, some of these temperatures, that plastic transitions temperature is above room temperature, and that means at room temperature it is rigid, it is that glass state, and above that, when it hits that temperature above, then it becomes flexible. Some of them it's below room temperature. If it is below room temperature, what does that mean? That means at room temperature it is rigid. It is flexible. But when you take it down to some temperature that's below, it becomes brittle. So you take the temperature down, it becomes brittle. And I'm going to go through this one more time with words for the other one. If it is above room temperature here, okay, above room temperature, what would that mean? That means that at room temperature, it is rigid. But if you raise the temperature, it would become flexible. Okay, so that is the difference between the two, the glass transition temperature. Okay, this where it switches over between being a rubber and being in that brittle state. All right, let's talk about the next one. It's low density polyethylene. In low density polyethylene, what we have is you got these long chains of repeating units of polyethylene, okay? So we have our carbon, 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 and it's just hydrogens everywhere, okay? We just have hydrogens everywhere. But what happens is we end up getting some branching. Okay, so if we didn't have branches, then these long chains of carbons could pack together nicely. But as soon as you put these branches in there, to where some of them have got branches, then we can't put the next one right up next to it very easily. So it might have to be out here with its branches. And so this causes it to have very different properties than the high density polyethylene. Low density means it's lighter. There's a lot more air trapped inside of these spaces and these gaps that we see there. Now this was actually developed during World War II, and it was used as an insulation for electric cables. But what we use it for now is plastic wraps, trash bags, things like that. So next time you use saran wrap, you can think about low density polyethylene. It's going to have that number 4 in the triangle. So when we have our little recycle triangle, it's going to have the 4 in it. So if you see anything with a 4 on it, you know that it is this low density polyethylene. Here where we live right now, there's some plastics that our recycling company will take and some plastics that it will not take. I don't believe it will take this number 4. Why will they take some and not others? There has to be a market for the recycle of it. They have to find a place where they'll take the materials to use them for something. And some recycling, there's a glut in it, they can't really use it that much, and so nobody wants to buy that recycling material to use it. And others, it's very readily recyclable, they find a lot of stuff to do with it and they can get rid of it. So you have to be able to have a market for the recycled material in order to have a recycling company actually collect it. Okay, let's talk about rubber. We use the term rubber when we're talking about the transition temperature of plastics between its glass state and its rubber state. But rubber is actually the name of a type of polymer. What we have is double bonds that are still in the chain, so it doesn't get rid of all the double bonds when we do that. Now, in your activity that you did our last class, I had a challenging one for you to try to do. And this challenging one actually ends up making a polymer that ended up with a double bond within the chain. Okay, so what we have here is that double bond is separated by single bonds. So we have single, 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 and then a double. Okay, single, 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 and then a double. So that's what that's saying. So that's what happens in rubber. There's a plant that generates and produces this polymer, rubber plant, rubber tree. The problem with rubber is that when it gets warm, it gets real sticky. Okay. At room temperature, not too bad, but once it gets warm, it gets sticky. Vulcanization was kind of a cure for this problem. Charles Goodyear developed this process. It was a total accident. He was being messy and he dropped some sulfur into a vat of this stuff. But what he found was that this made that rubber be able to keep the properties it needed even at higher temperatures. So when it got warm, it maintained its elasticity without getting that gummy, tacky feeling that happens. And like I said, it was an accident. What it did is it took where those double bonds were and it was able to cross-link them together and make a connectivity between those carbon chains. I'll show you a picture of it, which are in your notes there. So we have one long continuous chain here. We have another long continuous chain here. And he dropped some sulfur into a vat of this that was heated up, and that sulfur ended up cross-linking one chain to another. So we end up getting links from one chain to another chain at various spots along the way. Synthetic rubber can be made by butadiene, and that's the one that I had in your activity. Okay, you take this guy and you do a polymer repeat of it over and over. So I have a carbon with a double bond, then a single bond, then a double bond, and then like this, okay? That's what we're repeating that unit. Then when we break the bonds and form new ones, we end up making that double bond form at every third with 3 singles and then a double. All right, so that is a description of various polymers that we've seen here. What I want you to get from this is you ought to be able to know some details about each one of those. What's the monomer if you saw the polymer? What's the polymer if you saw the monomer? But not only that, if I said, okay, we're talking about Teflon, tell me what the polymer looks like, what is the monomer that makes it up, you should be able to tell me that.